Welcome to the mass spectroscopy system. The mass spectroscopy system is divided into two sections. Number one is the manifold, where you keep your sample gas, and the other is the high vacuum portion, which is always kept at a moderate to high vacuum, since the RGA head, the mass spectrometer head, actually sits right inside it. In order to do a mass spectroscopy setup, the first thing you do is to evacuate the entire system to ultimate vacuum. That involves switching on the turbomolecular pump, leaving the RGA off, and opening all valves to the system so the manifold is taken down to what is otherwise a relatively high vacuum. Once you've achieved this high vacuum, you can run a background trace using a mass spectrometer to figure out what's left inside the system that hasn't been evacuated yet. The system's now been pumping for several minutes, and at this point we should have achieved somewhere close to our ultimate vacuum. In order to see what's left inside the system, we run what's called a background trace, and it simply shows us things like molecules that are clinging to the inside walls of the system, things that are left that you won't be able to actually get rid of. We activate the mass spectrometer, turn on the filament, and allow it to run a trace from 1 through 50 atomic mass units to show us what's left in it. If I scale the graph, you'll be able to see that the largest peak over here is in the 10 to the minus 6 pressure range, and other smaller peaks are considerably less, into the 10 to the minus 7 range. This peak over here, for example, at 2 atomic mass unit, is hydrogen, or H2 gas. Hydrogen itself is actually nothing more than a proton. It's called protium. And H2 is therefore 2 atomic mass units. At 18 AMU, we find water vapor, or H2O, one of the main contaminants right now inside the system. 17, we find an OH, and at 28, we find either nitrogen, N2, or carbon monoxide, CO. This represents all the things that are inside the manifold that we simply can't get rid of. We'll store this right now as our background trace, and we'll subtract anything here on that we take from this in order to figure out what's actually in our system. Now that we've stored our background trace, any trace that we run on the system right now should show a flat line of approximately 0. We see little glitches here. However, they're very, very small, relatively speaking. We can now put our sample into the manifold and, subtracting it from the background, find out what's actually inside that sample. The first sample I'm going to begin with is pure helium gas. What we do to sample any gas is close the manifold off and effectively isolates the manifold from the high vacuum system. We then use valves over here to inject gases into the manifold, usually filling it to about 2 torr or so. So I now have 2.2 torr of helium inside the system. In order to see what's actually in my sample now, I simply open up this needle valve to leak a very small amount of gas from this manifold into the high vacuum part. This allows this manifold to stay at a relatively high pressure of about 2 torr, and it keeps the head of the RGA well below 10 to the minus 4, which is its upper limit. If you allow the head of the RGA, which has a filament inside of it, to be exposed to high pressures, it'll probably burn out the filament, which is a very costly thing. As expected, a sample of pure helium shows only a single peak at 4 atomic mass units. This is the atomic weight of helium. which does not form any molecules of any kind. Normally we would have expected background peaks over here, but we've subtracted them using the background subtraction feature. This allows us to see only the gases in the sample independent of contaminants which were present in the system even when the helium sample wasn't in there. Now that we're done with our sample of helium, it's time to flush it out of the manifold and put a new gas into there. Before we do this, we first stop the RGA scan and ensure that the filament of the RGA is turned off. The filament, again, sits right in the path of the gases that are going to be evacuated. If you forget to turn off the filament, it will be exposed to high pressures greater than 10 to the minus 4 torr. And it's quite possible to burn out the filament. So we ensure that the filament is off before we evacuate it. Now, we simply open the evacuate valve in the manifold and note that the pressure in the manifold drops. We leave this valve open for several minutes now to evacuate the entire manifold down to ultimate vacuum. Following that, we can close the screen valve and inject a new gas sample into the manifold. Neon gas is an interesting sample since naturally occurring neon contains two isotopes, neon 20 and neon 22. Neon 20 makes up approximately 90% of all natural neon, neon 22 making up the additional 10%. Carbon dioxide illustrates the concept of fragmentation. Carbon dioxide itself, CO2, should appear at 44 AMU, which it does here. But a plethora of other peaks appear. These correspond to fragments of the CO2 molecule. For example, CO, O2, carbon, and oxygen monotonically. Air is composed of a mixture of gases, including most prevalently nitrogen, or N2, which shows up at 28, oxygen, or O2, and argon. There are also small fragments showing up here of both monatomic nitrogen and oxygen. Another feature of a mass spectrometer is the ability to act as a leak detector. When operating in leak detector mode, the mass spectrometer is locked to AMU4, which is where helium sits, and only helium. There are no known fragments of any molecule at AMU4. So pure helium from a tank is used to find this leak. And all you simply do is lock your mass spectrometer onto leak detect mode, and using a tube which is attached to a large tank of helium, simply waft it over all connections while watching the quantity of helium inside the system. When you get near a small leak, and even a very, very small leak, you'll notice that the helium levels will dramatically increase, and when you remove the helium, the levels go back down. So it's simply a matter of wafting helium over each suspect connector while watching the mass spectrometer. If the numbers go up, you found your leak. When you pull it away, if it goes back down, that's it. A lot of connectors, such as these connectors over here, have holes drilled in them exactly for this purpose. You take your helium and you inject it into that small hole, and once again, if the level of helium goes up, you found your leak. Be careful, however, in that some types of O-rings are permeable to some extent to helium. In other words, If you take helium and you waft it long enough over some of these O-rings, they will start to leak regardless, because some of the helium simply diffuses right through the rubber. In this particular system, these are all metal O-rings and metal connectors, so there's no fear of that happening. But again, if you have rubber O-rings, be careful. You have to go fairly quickly past them. If there's a leak, you'll see it shoot up in a hurry. If it doesn't shoot up in a hurry, don't sit there too long, or you'll detect helium and you may think you have a leak when you really don't. Here's a view of the output of the mass spectrometer in leak detect mode. You'll notice that the quantity of helium that's detecting is very low. I begin taking my helium and wafting it over all of the connectors in the system. And if we find a leaky connector, the amount of helium rises. If I pull away the helium, it begins to go back down. Bring the helium near the leak, it starts to rise again. Pull it away, and it goes back down. And we found our potentially at least, we found our leak. Now once again, be very careful, because if I waft helium at an O-ring, you'll notice that it'll very, very slowly increase. If it does this, it's permeating right through the rubber.